Are we on record? Okay, we're being recorded. Let me start. This is Saturday, June 29th, 2013. My name is Harry Lonsdale. We're having a video conference of 3 teams of origin of life experts scattered around the world, actually. They began their research under my sponsorship about a year ago, last summer, and we're having our first annual review of their progress. So I want to introduce everyone, because we are now starting to record this conference. We have in the UK the first team of John Sutherland of the Medical Research Council in Cambridge, England, and Matt Powner of University College London in the UK. A second Canadian-US team consisting of Peter Unrau of Simon Fraser University in Vancouver, BC, Paul Higgs of McMaster University in Hamilton, Ontario, and Niles Lehman of Portland State University in Portland, Oregon, and a third team consisting of Dave Deamer of the University of California at Santa Cruz, California, and Wenonah Vercoutere, who works at NASA Ames Laboratory south of San Francisco in California, and Veronica de Guzman, also of NASA Ames, and a gentleman Hussein, whose last name I don't know, but I assume, Hussein, you can hear me through Dave. And then finally, I'm being assisted here, nobly I might add, by a man you don't know named Stan Johnson. That's Stan, S-T-O-N, not Stan, who is the Ben Research IT guru. And I'm speaking to you from the Ben Research Facilities in Bend, Oregon, United States. A little bit word of background. All of the 3 grantee teams have submitted written reports to us covering their last year's work. We received those a few days ago. I presume you've now all seen and read those. And Jack Shostak, who's not here, couldn't make it today, has already seen those as well and sent his written comments to me, which I have forwarded on to the review team of Irene, Nick, and Ron. So I think we're, if everyone's queued up and ready to go, we'll start. As for format, I thought the UK team would go first since it's already late in the afternoon there, followed by the Canadian-US team, followed by the US-California team. I thought we might take perhaps a few minutes break between each presentation. Each presenter, I hope, will present not only their results for the past year, but also their proposal for continued research. So we'll take a break between presenters. And if you want to ask questions, I propose, even though there's, I think, a block on your screen whereby you can type questions in, I would suggest if you want to ask a question, just say question, and the questioner will be recognized, and we can proceed from there. Are there any questions now before we begin from anyone?
Harry, I have a technical question.
Go, yes.
Which is that if we give you a PowerPoint presentation, for me to do that most easily, I share my desktop with you. But that will mean I won't be able to see the chat line that's going on. So technically, it might be worth just saying that if anybody wants to ask a question or interrupt, could they do it by using the audio?
John, I'm just realizing there's a bit of an echo in your speech. Would headphones help? Do you have a headset available?
I don't have a headset, no.
Okay, well then we'll do what we have. So
let me make one suggestion, and I understand what you're saying, John, and I think that the audio questions would definitely be the way to go. That way you can catch everything. But my one suggestion would be that if you're not presenting and you're not intending to speak, please mute your audio. There's a lot of background noise that happens if you're not muted, if you're typing or you know, making notes. All that kind of comes through and will be on the recording. So if you're not speaking and you're not going to ask a question, I would propose to go on mute, if that's okay.
Okay. Let me just see where mute is.
You should be able to, from your control panel, actually. Let me get back to that screen there. You should be able to, right next to your name, on that control panel, you should be able to hit the little microphone icon that will automatically mute you.
Now you can hear me again. Right, okay, I'm with you.
Yep.
But my problem is that if I actually have PowerPoint in full screen mode, then I can't see this control panel. The alternative is to do PowerPoint not in full screen mode, but then the slides don't work so well, huh?
Yeah, and I think you are right in the fact that if people have questions, they just need to speak up instead of chatting, because you, like you said, you won't be able to see the chat. So yes. if there are questions needed, then audio is the way to go.
So why don't we just give it a whirl, and if there's a problem, someone say there's a problem, and I'll stop.
John, give it a whirl. You're on.
Okay. So, Harry, I thought I'd give you a bit of an introduction first. Just to say that, can you see this now? No. Let me just press the share my desktop. So I've just tried to press the share my desktop button and it's not active.
We're gonna make you the presenter. Give me 1 second here.
Okay. Now I can share my desktop. Brace yourself.
Ah.
Right. Wow.
John, you now have full screen on my computer.
Wow. I have control.
You're in charge.
Love it. Okay, this is really good. I can actually do full screen and I can see what I want to see. Okay, so the story is basically that when you think about this, you tend to think of it either biology down or chemistry up. But when you think biology down, you end up still with an irreducibly complex, or apparently irreducibly complex scenario, whereby you have a need for informational molecules in the system to give you Darwinian evolution. You need building blocks and energy. You can't make or replicate anything without catalysts. And there's no point in genetics or metabolism without compartments. So when you think back down from biology, you get this picture of a cell, which is still a pretty complicated thing. And if you then try and imagine how it might produce chemically, there's huge demands on hypothetical prebiotic chemistry. Surely different chemistries are needed to make the various bits and pieces. And I think the biggest issue is surely these different chemistries will interfere with each other. So what people have tended to do to simplify the problem is to say, look, you can't have all of that together because it's too complicated. So depending on your predilection, you can imagine that one of those subsystems would have come first. So there's a bunch of guys out there who like RNA, but they say, you know, RNA must come first. Other guys who are more predisposed towards metabolism, so they guess that it might have come first. Likewise, some people say proteins first, and others say membranes first. And so the origins of my field has really been split apart over the years into various factions who are all putting forward the view that their preferred subsystem came first and then somehow invented the others. If you think from the chemistry perspective, you automatically think back to the famous Miller-Urey experiment, which was using lighting in a reduced atmosphere as an attempt at simulating what could have taken place on the early Earth, with this brown slime from which a trace amount of a couple of amino acids can be isolated, and parts per million of a few others. But in fact, when you think about the possible geochemistry, you could have had submarine vents or drying lagoons, atmospheric aerosols. There's a whole lot of possibilities that you could have had. And then you say, well, would the conditions have been static, you know, like sort of continuous warm weather like the American Southwest, or would it have been a sequence of different conditions like pretty wet, very wet, slightly wet, like the UK? There's really insufficient constraint from geochemistry to actually say what the conditions were and therefore to inform your search as to what came first. Can you guys all hear this? See this?
I can hear you, John. You're a little, I can't hear you very loudly.
Okay, I'll try and get a bit closer. Is that better, Peter?
Yeah, I can definitely hear you before, and now it's clear.
Okay. Everyone else okay?
John, I don't hear you well, but your graphics are so good that I can, between the graphics and your presentation, I'm following it quite well. Thank you.
Okay, Harry, I'll keep going. So what we've been doing recently, and in fact the whole point of the proposal with Harry was, now that I've reached 50 years old in my life, was to try and reconcile these different opinions and to say, look, one of these groups actually makes some good points. So why don't we take the good points and stick them all together and actually try and see if we can get the whole lot? Because the assumption that the chemistry must be too difficult or too overlapping and so on has simply been an assumption. It's not been experimentally demonstrated. So what we're going to do is use synthetic organic chemistry to systematically investigate all of this. If we find common starting materials or conditions, we'll try and use the commonality of things to merge the subsystems together. And then we'll look for geochemical scenarios that can support multiple subsystems and assess other chemical consequences of those implied scenarios. In other words, once we get a good idea about what the sort of situation was that gave rise to this, then we ought to be able to use that information to inform the chemistry. And then we'll try and put all the bits and pieces together and go, go shit or bust, basically. The last point to make as a general comment is what sort of chemistry we should be used. There is the Meteorite type chemistry I've just mentioned, which just makes millions of different things because it's pretty indiscriminate. And on the other side of the equation, there is this manifold A plus B goes to C, which is so beloved of mainstream chemists because it's easy to analyze what's going on if you only make one product, plus you can sell a single product. So most organic chemistry has grown up around this, but in fact it's not really appropriate to origins of life because origin of life does not correspond to the production of just one substance. So what we really want is something in the middle where, and you guys are American, I apologize for putting something French up on screen, where you want to have chemistry that's sufficiently complicated that it can go in the direction of evolution without being so complex that it goes off in this direction of labyrinthine complexity. So sailing close to the wind, we call it systems chemistry. So let's just start thinking about that from the perspective of RNA. So the key thing to emphasize here is that I'm not saying that I'm interested in RNA because I only want to have RNA. I'm interested in RNA as part of the greater picture. So we're going to have RNA, protein, lipids, and metabolism. And I'm just going to focus the discussion for a moment on RNA. Because when you look at RNA, if you're not a card-carrying organic chemist, you see something which looks pretty complicated. And so when you think about how it might have been made, you're struck by the fact, first of all, it's a string of repeating units, and I've cartooned these repeating units just to make the points rather than to obsess about the molecular details. So when you look at a nucleotide, which is the repeating unit of an RNA strand, nucleotide looks to you like a nuclear base attached to a sugar, attached to a phosphate. And you tend to think of it in those terms because most universities teach sugar chemistry separately to heterocyclic chemistry. So you've been trained, you're the victim of your own training, and so you look at this and you see a hybrid of a sugar and a nuclear base joined together by this bond. When you think about the most obvious way in which that could assemble, you're right to, first of all, investigate the most obvious way. The most obvious way is for a sugar and a nuclear base to have had a phosphate attached, and then this red-blue sugar nuclear base should have been produced by putting the red and the blue bits together. And the blue bit could come from two smaller blue bits, the red bit could come from two smaller red bits. That seems to make quite a lot of sense as a good first thing to try. And people have tried this for many, many years, and it doesn't work so well if you want to make the natural nuclear bases attached to natural sugars, i.e. if you want to make the real molecule. Why doesn't it work so well? Well, the reaction that's normally sold, if you like, or touted as the way of making the red bit, the ribose, is a reaction where you take the simplest carbohydrate, formaldehyde, and you treat it with calcium hydroxide and warm it, and you actually get a whole mixture of sugars, one of which is actually ribose. The mixture of sugars tastes sweet. Can you believe it, Harry, when this was done in 1862? The person that did it tasted it and recorded the taste in the paper. This is not something you're allowed to get your students to do these days. Although I suspect we've all had students that we would not mind too much if they did taste certain reaction products, okay? Now, the problem with it is that it's not selected to make ribose. It makes lots of other things. That's called the formose reaction because formose is the name that's given to complex mixture of products. In fact, you get a sea of products over 50, and ribose is a very minor component, actually. And try as they might, people have not properly resolved the difficulty with the formose reaction. And in fact, even if they did, the late Bob Shapiro pointed out quite rightly that even if you could solve the formose reaction problems, you've got additional problems because the nitrogenous substances you need to make the bases would react with the sugars and the intermediates in undesirable ways. And what he's saying is that this blue thing, so hydrogen cyanide, the simplest blue thing, if you like, the Germans call it Blausauer, blue acid. And so hydrogen cyanide basically, if left to its own devices in the presence of aldehydes, reacts to give these red-blue hybrids. So in other words, what Bob Shapiro is saying is even if you can make sugars that way, you're going to have problems if you have the blue bits you need to make the bases, because they're just going to interfere in undesirable ways. Even if you could do that, when it comes to the natural nuclear bases, the pyrimidines can't be joined to the prebiotic to the sugar, and the purines can only be joined with great difficulty in a really messy way. So this doesn't work. So a couple of years ago, before Harry got involved in this, we showed an alternative option, which is where you start with half a sugar, half a nuclear base, and phosphate, and you make something where you join these two bits together before you add the other half of the sugar and before you add the other half of the nuclear base. And then you add phosphate and you end up with this unit. So the idea is you start, instead of preforming the base and preforming the sugar, you actually take half a base, half a sugar. When I showed my wife this slide in cartoon terms, she said to me, "Is that all you do, John?" Okay, because it's not really particularly impressive. If you look at it in molecular detail, it looks at, you can see it in its molecular detail, but I think the point is made by the cartoons, actually. Now, again, there's a slight problem with this. When people look at it, they say, look, that's a multi-step organic synthesis that you have operated in the laboratory, and you're now trying to tell us that this could have occurred on the early Earth. And again, Bob Shapiro, he was very good at vocalizing the problems that several people have with this sort of approach. And so in talking about this in general, he had said the analogy that comes to mind is that of a golfer who, having played a golf ball through an 18-hole course, then assumed that the ball could also play itself around the course in his absence. And the reason that analogy works is because you think of a golf course and it looks a little bit like a free energy surface. And a free energy surface is a surface which molecules have to traverse as they go from one part of the reaction pathway to another. And so if you've got a free energy surface that looks like a golf course, there's no reason why a ball would go in only one direction unless a golfer was playing it. But the thing about free energy surfaces is they're not always relatively flat. They can be quite steep. In fact, they can be really steep. In fact, if you look at certain golf courses have very steep features. So if you look at the cliff top where the golf course is, you can imagine that there's no way the ball would play its way around without a golfer. But if you put a golf ball here, you can well believe that that golf ball will make its way down the cliff onto the beach without the golfer doing anything to it. And
John, I've already done that, by the way. I've done that once or twice. Sorry.
I bet if you want to find, if you go down on that beach, you'll find quite a few golf balls, right?
Right.
That weren't put there deliberately by French golfers. So we've gone some way towards getting this, but we've not solved the problems. We've got to find out how to do this with the purines, and we've got to find a way of stringing these things together to make longer RNA. Now, we had some success with this recently, at least a contribution to the area of how you might solve this problem, which we published just recently in the journal shown at the bottom. I'm not going to go through that because there's a lot of other stuff to talk about today. What we've now been thinking about is actually where do these building blocks come from? Because for the RNA subsystem, we're making progress, other people are making progress, and collectively I think we're making quite a bit of progress. But we need to sort out where these building blocks come from and look at them. Sugars, these high energy molecules, phosphate and so on, we need to sort out the purines, and we need to deal with this problem that hydrogen cyanide reacts with sugars in undesirable ways. So we got into this last section, if you like, by reading some papers by an American group and an English group that said you can get phosphate by taking an alloy, or basically iron nickel phosphide, leave that in water, it undergoes a very interesting corrosion reaction or disproportionation reaction, and you get an iron phosphate. But the phosphate that we need for RNA synthesis, we need soluble phosphate, and this is insoluble. And so we wondered if we could actually solubilize it by allowing it to react with atmospheric hydrogen cyanide. People in the past, in the literature, have suggested that iron 2+ ions would react with cyanide and concentrated in the form of ferrocyanide, these cyanometalates.
John, a question, John? This Schreiber site that you referred to, does that exist on planet Earth, but does it only arrive here on meteorites?
Okay, so that was thought until very recently to be the case, but Matt Pasek, in conjunction with Roger Buick, has very recently published showing that there's a smoking gun evidence for Schreiber site, basically, in 3-point-something billion-year-old rocks. So they find low valent or low oxidation level phosphorus in these very ancient rocks, suggesting that either there was an awful lot of meteoritic delivery of Schreibersite, or that there was some endogenous Schreibersite on the early Earth. So I think it's a subject for debate, but it's kind of interesting because whether it's right or wrong, it got us into some quite interesting chemistry. So hydrogen cyanide then would give us these cyanometalates, and we hoped at the same time it would solubilize the phosphate. And for a variety of reasons, we wanted to consider that chemistry in the context of metal sulfide. So we've been recently getting into the chemistry of these cyanometalates, and this is stuff that's been looked at by physical and inorganic chemists before, in particular the UV photochemistry of these cyanometalates. So there's physical chemists and inorganic chemists have looked at the photochemical behavior of transition metal cyanide complex, but they've been looking at it from the point of view of their own subject areas. Of course they did. And so the inorganic chemists were interested in what happened to the metals as they go through these various photo redox cycles, and the physical chemists were interested in the photophysics of this. We were interested in it because we could see a cycle where essentially ultraviolet light is coupling two hydrogen cyanides together to give cyanogen, which is an oxidation reaction. And in the process, it's generating electrons. And electrons are very potent reducing agents. And so we were attracted to what would be happening with those electrons in the presence of hydrogen cyanide. And to cut a long story short, we found that we actually, if we just took hydrogen cyanide solution, put a bit of copper cyanide in it, and irradiated it, we got a remarkable spectrum. And that spectrum basically is a NMR spectrum. That's a method we use as organic chemists to investigate what's going on in reactions. Essentially, we could see that we've made some pretty interesting organic compounds, and we could make synthetic standards of those compounds to prove what they were, and it turns out that they were derivatives of 2 and 3 carbon sugars. In other words, hydrogen cyanide, when you shine a light on it in the presence of copper-1, generates 2 and 3 carbon sugars. And it does it, if you're a chemist, you know, interested in the mechanism, you can see it on the left, but I've just outlined it on the right. What happens is this blue triangle, the nitrogenous molecule, is reduced by electrons to formaldehyde, or to the precursor of formaldehyde. And then what happens is exactly what Bob Shapiro told us would happen, that the red guy reacts with the blue guy. So this has American political overtones, Harry, doesn't it? A blue guy being converted into a red guy, I guess, isn't your sort of political desire. But here's a blue guy and a red guy getting together, which I guess is pretty rare in the US these days. Anyway, this blue-red guy, it's exactly what Bob Shapiro warned us would happen. But then the key thing about this chemistry is that the electrons then reduce the blue-red hybrid into half a ribose, into the 2-carbon sugar. So some of this then reacts with additional hydrogen cyanide, gives another blue-red hybrid, and that then gets reduced to give the other half sugar. So essentially, we turn hydrogen cyanide into the half the sugars, the 2-carbon and 3-carbon sugar fragments. Now, it turns out we need hydrogen cyanide for that process. We need potassium cyanide for that process as well, ideally. And we started worrying about the fact that we needed quite a bit of cyanide. And we found this chemistry which basically concentrated cyanide in the form of ferrocianides. And we then looked back and found some very interesting early Russian chemistry where they heated ferrocianides and shown that they thermally decomposed back to cyanide. So imagine, if you will, that you've got ferrocyanide and you heat it with either geothermal heat or meteorite impact heat. You can turn it back into potassium cyanide. And it's quite exciting, actually, because if instead of having, or as well as having sodium or potassium ferrocyanide, you also have magnesium ferrocyanide, magnesium ferrocyanide does something different. It's converted into magnesium nitride. And magnesium nitride is actually a precursor of ammonia. Lastly, if you take calcium ferrocyanide and heat that, calcium ferrocyanide is converted into calcium cyanamide. So it turns out, depending on what the counterion is, these ferrocyanides are converted into cyanide, nitride, or a precursor of ammonia, and cyanamide, which is what we need for the RNA synthesis. So we then started thinking about what would happen if we did this in the presence of metal sulfides. And it turns out that metal sulfides are, I think, the key to this. So if we took our phosphate and cyanometallate and evaporated it and then heated it to high temperature, we could see that from that Russian literature, we'd end up with metal, phosphate, cyanide, cyanamide, and nitride. If we then added a little bit of water to that, so imagine that you've evaporated a body of water, a pond or a puddle or a lake or something, you've dried it out, and you then heated what was evaporated at the bottom to 700 degrees centigrade, and you then add back a bit of water through rainfall, you end up with a solution containing cyanide, cyanamide, and ammonia. And it's known that cyanide will react with metal sulfides. It dissolves them. It's used in mining, in metallurgy, and so on. And the cyanide then would react with the metal sulfides and liberate hydrogen sulfide, or hydrosulfide, HS-. And so that then struck us as being something that would actually be a reductant for this copper photoredox chemistry. And so we've rerun this photoredox chemistry now using hydrogen sulfide, and it does just what it did using hydrogen cyanide, except for a little trick, which is that we actually get some, what I've called over-reduction. We make a 2-carbon sugar, and a bit of it gets reduced to acetaldehyde. And so what's nice about it is that we make the 2 2-carbon sugar. And if we then add cyanide, we can then get to an intermediate here, which we can then further reduce to the 3-carbon sugar. But seeing the acetaldehyde also being generated in this chemistry made us think, well, we ought to think about what would happen if that reacted with cyanide, because it would give this compound here, and if that then got reduced, it would give this hydroxyaldehyde. And at that point, we started to see a connection between the RNA chemistry and amino acid chemistry, because if you look at this hydroxyaldehyde here and add hydrogen cyanide and ammonia, you can see it's actually the precursor, the so-called strata precursor of the amino acid threonine. And then this cyanohydrin here is the precursor, if you react with ammonia, to alanine, this one to glycine, and this one to serine. So it looks to us as though when you start running the chemistry to make these sugars that you need to make RNA, you automatically get 4 of the amino acid precursors. Or at least that's the way it looked until a couple of weeks ago, a couple of months ago. Because we've now extended this, and we've extended it additionally by saying, look, if we now look at our RNA synthesis, we can see that hydrogen cyanide is actually going to make the sugars we need. And it's actually going to make the 2-carbon sugar before the 3-carbon sugar. And all we need to do is to add hydrogen cyanide here to convert a bit of the 2-carbon sugar to the 3-carbon sugar. But remember, in this synthesis, we wanted to add cyanide at that point as well. So we've still got the problem that we've got to find a way of adding cyanamide here and adding cyanoacetylene here. But it turns out that copper can come to the rescue because it's known that copper reacts with cyanamide and ammonia and gives an insoluble precipitate, so-called solid coordination compound. And it turns out that cyanoacetylene also, strangely enough, forms a solid coordination compound with copper. So if you like, you can just make these solid copper coordination compounds and keep them, and they're indefinitely stable. And so if you then take a mixture of these 2 solids at the bottom of a beaker, you can actually liberate those reagents from those solids by adding hydrogen cyanide. So when we add the hydrogen cyanide that we need to restart the conversion of the 2-carbon sugar to the 3-carbon sugar, it turns out we can liberate those reagents, but they're liberated in a particular order. So the least stable complex liberates its ligands first, and it turns out that the cyanamide that you need first is released first. And then add more cyanide, and you can release cyanoacetylene. So it turns out that the reagents can be delivered in exactly the right order you need for RNA synthesis from these copper coordination compounds. We've now investigated this copper chemistry far more extensively. And on top of that, we've actually investigated how we might make lipids. So we've now found a connection between RNA and amino acid chemistry, suggesting that the RNA and the amino acid or peptide subsystems might be linked. So I'm now going to get greedy and say, can I have phospholipids too? And we wondered if we could take glycerol phosphate and an activated carboxylic acid and somehow get that carboxylic acid to react with the phosphate and then end up deposited on these alcohols. And it turns out that reaction didn't work, which was unfortunate. But we started thinking, well, hey, we've tried doing it with glycerol 1-phosphate. How would we get glycerol 1-phosphate in the first place? Well, we'd get it by phosphorylating glycerol. And I'll leave for a minute the issue of where the glycerol would come from. But if we did have glycerol, we've now shown that if you phosphorylate it, you get the cyclic phosphate, and if you hydrolyze or allow the cyclic phosphate to hydrolyze, you get a mixture of the 1-phosphate and the 2-phosphate. And if you acylate the 2-phosphate, it turns out it's now a much better arrangement. You've got primary alcohols to receive the acyl group, and lo and behold, this chemistry works really well. Synthesize mixtures which contain monoacyl and diacyl phospholipids. And if you just take a microscope picture during the chemistry, you add a dye to stain what happens. You can see that you start generating membrane vesicles. spontaneously out of these reaction products. So if we can make glycerol, we've then got a way of adding phospholipids on top of the RNA and amino acids that we've generated. So now here's the big picture, okay? This is a scary picture, and you probably can't see the details. But I'll give you, can you see this magnifying glass?
Yeah.
Okay, so here's where we start with hydrogen cyanide over here on the left. Hydrogen cyanide, sometimes half of the cyanide hydrolyzes to formamide. But it gets converted to the cyanohydrin here. There's glycine, there's the 2-carbon sugar I showed you about. There's the reaction to give acetaldehyde going up to give alanine. And there's the reaction I just showed you, which is the precursor to threonine.
John, excuse me, John?
Yep.
And the lightning bolts are?
The lightning bolts indicate the photochemical reaction in the presence of hydrogen sulfide. If it's got a blue hydrogen cyanide, it's the photochemical reaction in the presence of hydrogen cyanide.
So they're photons or something?
Yeah, so these are light-driven reactions.
Okay.
So there's the 2-carbon sugar I told you about, and there's its reaction with hydrogen cyanide and the reduction to give the 3-carbon sugar, and then fed into the RNA synthesis that I showed you. But let's now have a look at this 3-carbon sugar. It turns out that if you leave that in the presence of phosphate, it gets isomerized to a different 3-carbon sugar, dihydroxyacetone. Now, the strict organic chemists in the audience won't be surprised by that. What did surprise us was that when we apply our reducing reaction to dihydroxyacetone, it gives 2 products. It gives glycerol, that I've just told you we need to make the lipids, and here's the reaction that goes off to make the lipids. But it also makes acetone. Acetone looks like a prebiotic product in this chemistry. Acetone then reacts with hydrogen cyanide, makes a cyanohydrin. That cyanohydrin goes through this same sequence of chemical events and makes another aldehyde, which, when it reacts with cyanide and ammonia, gives me a precursor, the Strecker precursor to amino acid valine. That aldehyde can then be homologated again by the same sort of chemistry. We go through an iteration process, and we get the precursor. You can almost see it up there, to the amino acid leucine. So we're now up to 6 amino acids of the natural 20 amino acids. Down here is the reaction of cyanoacetylene, which we showed was required to make the nucleobase in the RNA chemistry. And I just told you that we could release it from its copper complex by adding hydrogen cyanide. But if we add excess cyanide, the excess cyanide starts to react with the cyanoacetylene, and we get these 2 molecules here, one of which is a precursor of aspartic acid and asparagine, 2 other natural amino acids. The other guy gets reduced to give this dinitrile, and this dinitrile then gets reduced further to an aldehyde. That picks up cyanide, reacts with ammonia, and we get the precursor to glutamine and glutamic acid. So we're now at 8, or actually 10 amino acids. Finally here, the cyanoacetylene reacts with phosphate. That's been long known to give this thing cyanovinyl phosphate. But it turns out that cyanovinyl phosphate is reduced by the reducing reaction to give cyanoethyl phosphate. And cyanoethyl phosphate reacts with more cyanoacetylene and gives us acrylonitrile. Acrylonitrile then reacts with ammonia and cyanamide to give this amino propionitrile and in admixture with cyanamide. And if you then add hydrogen sulfide and turn the light on, you get these 2 molecules. The top one then goes through the iteration, the same sequence I've shown you before, and it gets turned into the precursor to proline. And the lower one of these structures then goes through the same sequence of reactions and is converted by exactly the same sequence of reactions into this guy down here, which is the precursor, the Strecker precursor to arginine. So if you look at these reactions collectively, we think we can call it quite rightly or justifiably a proto-metabolism. So we've got a metabolism, or protometabolism, that's furnishing RNA building blocks, protein building blocks, and phospholipids for membrane building blocks. In other words, by taking this attitude that we should start reconciling the four various camps, we can now find that they're connected at the level of this photo-redox chemistry, this chemistry of solvated electrons. And we're quite excited about this. We've not published all this yet. We're rolling it out slowly. And where do we want to take it? I just have to point out, Harry, that there's your name. We acknowledge you when we talk about this now. You know that this requires a lot of people to work on this, and there's been a lot of people over the years, and your money has gone to support this lady, Dr. Claudia Percivale, who's worked on a lot of this chemistry that I just told you about. But finally, you asked me if I'd say where we were going to go, next, and I'll just.
John, could I interrupt one more time?
Sure.
I must say, when I saw that huge, complex graph of yours, even though I looked at it fairly hard a couple of times, I never understood it at all. But I do, thanks to your oral presentation. But forgive me for attempting at a joke. But I'm wondering, when you looked in your flask at the end of that, did you find a bacterium, or better yet, did a frog jump out of your flask? That's supposed to be a joke.
Nothing has come out of it yet, Harry.
Well, keep looking.
We're hoping one day something will.
Well, you have all the parts. All you need is a self-assembly.
I'm joking, Harry. Yeah, so that's the point, actually. The next point to make is that there's this lovely quote out there that George Whiteside basically points out that it's a long way from slime to Mozart. What his point is when he's saying that is that, you know, the chemistry doesn't have to make Mozart. It just has to make the most primitive life form. But in fact, it's just amusing. Donna Blackman, a friend of ours, you know, she's quoted George on this. And here's your picture. There's Wolfgang Amadeus on the right, and that's polycephalum physarum, which is the slime mold on the left. Okay, and George's point is that they're distant, but in fact, if you look at them on the phylogenetic tree, slime molds actually occupy an adjacent branch to animals, including humans. And we want to trace all the way back to something simple. And the point for saying how similar these are is not to have a go at George. It's basically because in the context of what we're thinking about here, going from hydrogen cyanide to life, then there are two things you have to do. You have to advance in this direction along the axis which I've labeled synthetic complexity. But you also, at some point, have to go up this axis, which I've labeled as aliveness. And I think what guys like us are doing is progressing, you know, in little bits along this axis here. And what we've got to think about now is how to go up. And I think a lot of us have, for many years, have thought the key to this is getting into polymeric systems, particularly those which are capable of replication. But I think what has been holding us back to a certain extent has been not knowing which building blocks would be available when you come to make polymers. So I think we're beginning to see, when we start thinking about peptides and proteins, we can have quite a large number of the amino acids of extant biology. And if we can make the purine ribonucleotides, we can maybe actually also have, you know, RNA in the conventional sense as it's now found in extant biology. We've got phospholipids, so we've got constrained systems. And so I think we're now thinking about how do we go up a little bit. And that's what we want to work on next. Because for sure, the trajectory from HCN to these living things is not a linear trajectory, you know, it's not a diagonal line. And we don't think it's all the way along here and suddenly jumping up. We think it's more likely you go along a bit, up a bit, along a bit, up a bit, and so on. So that's where we're going next. And everybody.
Thank you, John. Questions?
So could I have a question here? Deamer? is.
I presume everyone can hear everyone. Go ahead, Dave.
John, I think I detected a couple of essentials in that. I want to make sure that I got it straight. One essential is illumination. There has to be wavelengths of light that will interact to at least activate your photometabolism. Is that correct? You need light a certain wavelength.
That is correct, Dave. So we've been doing this using a lamp with principal emission of 254 nanometers, and with no ozone on the early Earth, and albeit a lower overall radiation flux from the sun, the physicists tell me the UV flux from the sun was actually higher 3.8 billion years ago.
The follow-up question is that you must have land masses for this to work. You have to get your chemistry up out of the ocean and into some sort of presumably volcanic land mass. Is that correct?
We need what we ideally want, Dave, is a body of water which is shallow and which can dry out.
Okay. So the body of water then also has to be in contact with some copper mineral to make this work. Is that correct?
I should point out that the copper for the photoredox chemistry is catalytic, and it's in fact incredibly active catalytically. So for that aspect of the chemistry, you don't need much. If you want to store up large amounts of cyanamide and cyanacetylene, then you can actually, there are other ways of storing it, making iron complexes. But we like the copper ones because they're solid, and that has some convenience actually. But yeah, you need to have some copper. But copper is found on the Earth now, so I don't think it's too big an ask to have copper on the Earth then either.
Final question, is the light an activating photochemistry, or is light energy being captured by the process that you've described?
What happens, Dave, is that you published a paper many years back on using irradiating ferrous cyanide in vesicles. Yeah? So if you irradiate ferrous cyanide with long wavelength UV, it photoequates, it loses the cyanide ligand. If you irradiate at lower wavelength, what happens is you kick an electron off the iron into solution. So you go from iron 2 to iron 3, and you get an electron in solution. And it turns out that iron does that. It's not particularly efficient, but copper cyanide does it incredibly efficiently. It spits out an electron, so you're harvesting the photon energy and generating the energy associated with a solvated electron, which has a reduction potential of minus 2.2 volts. So you're generating an amazingly potent reducing agent in response to a photon.
I like your systems approach, and I really agree that we have to try to work toward a more holistic approach in all of our work here. Thank you for your talk.
My pleasure, Dave.
Other questions?
Can I ask a question here? Oh, go ahead. Oh, hello?
Hi there.
Okay, I guess I'll go ahead. So I was wondering, John, if you could see any shadow of the reaction network that you presented through the kind of biology down approach. Maybe, I know people have made speculations about which amino acids are primordial. Does your synthesis kind of line up with that?
So if you look at, you're familiar with this paper by Krishnamurthy, where he sums up all the previous suggestions, comes up with a consensus order. So the only one of the amino acids we've got that he doesn't have is arginine. It turns out arginine, people say it's got a complicated side chain, but it's a side chain which is derived from cyanamide. So the side chain of arginine is no more complicated than ornithine plus cyanamide, actually. But yes, it links up, Irene, with what you see. The other thing that strikes me as surprising is that when you look at sort of most discussions about which amino acids biology uses, people tend to say, well, look, you know, prebiotic chemistry must have made hundreds, and then biology has chosen to use a few it does. But what we're finding is that there are very, very, very clear chemical indications that at least 12 of the amino acids used by biology are connected to each other by the fact that they can be synthesized very readily by this sort of, it's a Kiliani-Fisher type reductive homologation reaction, which is a reaction which I don't think most of us expected would be a prebiotic type reaction. But it turns out that it happens. You just take cyanide, copper, 1, and light. So that's pretty simple, actually.
Cool, thanks.
Questions? So, Veronica?
Yes. Can you hear me?
Yes.
Hi. So, John, my question was with regard to the heat indicated on your flow chart. Is it always on the scale of 600 to 700 degrees C?
If you want to decompose ferrocyanides, the answer is yes, we simply need that high temperature. But we like it simply because it's a very good way of generating cyanide, dry potassium cyanide. And then if you add a small amount of water, you can have really concentrated potassium cyanide, which Volta does, but quite a lot of other people would like to have. So Rand, for example, published a really nice paper in End of Antiquity with Greg Springsteen, pointing out that if you take cyanide in formamide salts, you can actually get pretty decent yields of some of the purine bases. Other people have done similar things with formamide as well. Lots of people have. But the point is that when you first look at that, you think, you know, how am I going to get loads of cyanide in formamide? And because you get formamide, you really need to have cyanide and high-quality cyanide in formamide. But heating the ferrocyanide to a high temperature, you feel a bit uncomfortable invoking a high temperature. But the reward you get for feeling uncomfortable is so useful, or so nice from a technical point of view, that we figure it's in, you know, head, if you like.
Thanks.
Okay.
Other questions?
I have a question. This is Peter. Speaking. My impression was that meteorite samples have a pretty broad array of organics in them that perhaps could be matched up to the kind of synthesis that you're describing as photochemistry that is taking place in aqueous meteorite conditions during the early formation of the solar system. So I'm just wondering if any of the metals in the meteorite samples have any potential, from your perspective, to be the kind of chemistry that would lead to the organics that are actually observed in those meteorites.
So, can I show you 2 more slides? I'll show you 2 more slides because that will answer your question very clearly. So, what this is, Peter, is a picture of the Canyon Diablo meteorite.
I don't think I'm seeing anything yet.
Okay. And I should be sharing my desktop still.
I see it, John.
You see a picture of a meteorite?
Yes.
I see a picture of John. Or I see the John video.
You know, I'll explain it to you, okay? So here's a meteorite, the Canyon Diablo meteorite. These meteorites contain these inclusions. They're like the size of a thumbprint, but they're everywhere, and they're in all these iron nickel meteorites. And the inclusion is essentially metal sulfide. It's iron and nickel sulfide, containing also in some cases copper and zinc. And it's surrounded by a thin layer of schreibersite. So the schreibersite that's found in meteorites almost always surrounds transition metal sulfides. okay? And if you look, for example, using various X-ray-based methods and look and see what's in some of this meteorite debris, you can see sulfur, iron, cobalt, nickel, copper, zinc. So we actually, one of the scenarios we're very interested in is that when you get meteorite impact on the planet, that debris will actually have the Schreiber site right next to the transitional sulfides. And if you actually then start getting water into those cracks and so on in meteorites, and then heat them and radiate them and so on, you could actually do the chemistry on meteorite, in fragments of meteorites. An alternative scenario is lake beds, as I've said. But yes, the geochemistry that's suggested is not completely pinpointed, but I do think there is a connection to a lot of chemistry that takes place in meteorites.
Thank you.
Yeah.
John, can I add to that? The Schreiber site continues to intrigue me. Is it your position that we wouldn't find any Schreiber site in nature on the surface of the Earth because it'd be unstable in an aqueous, oxygen-containing atmosphere? Is that why it isn't around?
Yeah, absolutely. So it corrodes and it gives phosphate and also phosphorus in oxidation level 3, phosphite. And so you can get phosphate in many other ways, but there aren't many other ways to get phosphite. So that recent discovery I told you about from Roger Buick and Matt Pasek is they found phosphite in very, very old rock. So the indication is that whilst there isn't any Schreiber site around now, for the reasons you rightly point out, there is a smoking gun in the form of phosphite that there having been Schreiber site early on, either delivered by a large number of the impactors or actually endogenous. And I spoke to Roger Buick specifically about this, and that's what he said, basically.
Can I make a comment?
Sorry. Oh. Someone wanted to speak? Nick?
Yeah, this is Dave Deamer. Can I make a comment?
Dave, yes.
These iron meteorites are the result of a melting process that went on in the asteroid belt in multi-kilometer sized early asteroids in the early solar system. The early Earth at the time we're interested in was in fact anoxic, so we would not have this kind of oxidation, and some of these same chemistries would have been going on in the melting process that the Earth was going through at this time, I would guess.
Sure, Dave. Yeah. So we're now talking to quite a number of geochemists, basically, and trying to refine the sort of geochemical scenario. We haven't yet focused in on one because I think the origin of life field tells you that if you focus in on one too soon, you can go wrong. But we're certainly basically ultimately hoping to do that because I think that will actually then back inform the chemistry.
So John, this is Harry again. Is it fair to say that 3.8 BYA, we needed a meteorite?
Well, it's one possible scenario.
Sorry?
Yeah, I wouldn't go so far as to say to make any certainty on this because what the chemistry tells you is what you need from a chemical point of view. You need transition metals, hydrogen sulfide, potassium cyanide. Well, if you have those, the chemistry is telling you can make all the bits that we can make. So that's what I'm doing is basically then suggesting to you that as far as I'm concerned, when I see that chemistry working to make those things, that I'm pretty happy about assuming that the chemistry is informing me that I need those things geochemically. To then go further and say it's a meteorite or it's happening, that I think requires we need to think more about that. And what we also need to do is to collaborate more with people who understand that sort of science better than we do. And we're trying to reach out to those people and do that, eventually.
Are there other questions?
I have one more comment on this, passing on something that Wenonah just mentioned, and that is that this same theory is what we call the late.
David, I cannot hear you.
Oh. Well, can everybody hear me?
Yes, I can.
It's very faint.
Okay, I'll try this again. The late heavy bombardment was occurring. The late heavy bombardment was occurring at the same period of time we're talking about, and meteoritic infall and cometary